next video. Let's get this out of the way. Okay, so last time we saw in 4.2 that we can estimate area. Okay, oops, we better get some focus as usual. These devices aren't dope like me. They can't stay focused. Like, you know, Dr. Flowers can stay focused. There we go. We got to remind it every now and then, you know? So in 4.2, we estimated area under a function over an interval. And we did that by putting rectangles underneath the function and adding up the areas of the rectangles. We found that when we put more rectangles under the function, then we get closer and closer to the area. But we never got the actual area. We've only estimated it. And in the problems I gave you in 4.2, it's only asking you to estimate it, either by using right-hand endpoints or left-hand endpoints. Okay? But what about the actual area? I'll remind you, we said what it was, and we attached a notation to it in the last video for 4.2. But I'll remind you again. Remember, the actual area would be you doing that infinitely often. So it'd be a limit of you, as the number of rectangles go to infinity, of adding up all the areas of the rectangles. So it'd be, if you're using left-hand endpoints, it'd be a limit as n goes to infinity. Again, we use summation notation to compactify the sum. N would go from 0, or sorry, I would go from 0 to n minus 1 of f of xi times delta x. Or if you were using right-hand endpoints, then it would be the limit as n goes to infinity of the sum. I would start at 1 and go all the way to the last one, n of f of xi times the change in x. And we agreed to call this limit of a sum a notation last time, but I'll remind you again. That was equal to this notation. You put the interval, you put an s-like figure, the two endpoints on the top and bottom, your function, and a dx. So instead of write this, or even say the actual area, we could say this. They all mean the same thing. And now the verbal name, it's called the definite integral. We said all this last time, just reminding you. Of f from a to b. Okay? So to actually compute this actual area, or this definite integral, we'd have to take the limit of one of these sums. Okay? That can, depending on the function, can be pretty nasty. Okay? So far we can only estimate the area. Yeah, in 4.2, but we can't find the actual area without doing one of these limits. Remember, that's been called this, and verbally that's called the definite integral. Okay, well, now we're going to find out a way to find the actual area, except we're going to do it without taking one of these limits. Let me ask you a question. Can you walk backwards? Let's say it again. Can you walk backwards? Yes or no? Yeah? You can walk backwards. Okay, how about this question? Can you think backwards? Can you think backwards? Well, if you can think backwards, then we can find the actual area under a function without taking a limit. Okay? Okay, so let's try it. Let's try to think backwards. Okay? Not forwards, no. Backwards, I said. Backwards. Okay, I'm going to make a definition. So there's the definite integral. I'm going to define something called the indefinite integral. Okay, here we go. You ready? This is a definition. Let f of x be a function okay. The what we call indefinite integral of f of x comma, let's attach a notation. It's written this way. Another s-like figure, and then the function here, and then a dx, comma. So that's the notation for it. The words are called indefinite integral of f. The notation for it is this. What is it, though? Well, I'm going to tell you. Is the most general function, capital F of x, okay, so that this happens, so that capital F of x differentiates to be f, okay? Okay, let's move it over so you can see it. Okay? So, the indefinite integral of f, the notation for it is here, is the most general, I repeat, most general function, capital F, that differentiates to be little f. So be careful, it's not taking a derivative, it's finding something that differentiates to be a given function. So it's not taking a derivative. Okay? Let's try some. Ready? Sure you're ready? Let's try to find the indefinite integral of 2. Okay? Well, let's see, I'd have to find a function that differentiates to be 2. Okay, well, there's a lot. Notice that 2x differentiates to be 2. So maybe the answer is 2x. Well, wait a minute. 2x plus 3. When we take the derivative, we also get 2. Ouch. Well, wait a minute. 2x minus 5 halves. When we differentiate that, we get 2. So you can see the most general function that differentiates to be 2 is 2x plus some constant, because constants differentiate to be 0. Okay, so the answer is 2x plus a random constant that we don't know, and a lot of times never will know, because we don't know what constant could have been tagging along here. Okay? Let's do another one. How about this one? The indefinite integral of 2x. Okay? So I got to find something that differentiates to be 2x. Well, let's have a look. Let's see. How about x squared? When we take the derivative there, we get 2x. So I guess the answer is x squared. Well, wait a minute. When we take the derivative of x squared plus 10, we also get 2x. So you can see the most general function that differentiates to be 2x is x squared plus some random constant. Like here it was 10. Okay? Now how did I come up with this? Well, let's see. Derivatives lose a power. So if I want to lose a power and just have a 2x, which has a power of 1, I had to have a power of 2. Thinking backwards. I had to have a power of 2. So that when I take the derivative, I lose that power and go down to 1, which is this x here. Okay? Let's try another one. How about the indefinite integral of x cubed? Can you think backwards on this? Let's see, derivatives lose a power, so it must have been x to the 4th, because when I take the derivative I get an x to the 3rd. But be careful, I get a 4x to the 3rd. I only want an x to the 3rd. So if I'm clever, I'll kill off that 4 when it comes down. So how about a 4th x to the 4th plus some random constant? Ouch. Okay, so when you take the derivative of this, the 4 comes down, kills itself with the 1/4, and leaves x cubed, and the derivative of the constant 0. So the derivative of this is this. Ouch. Okay, so let's make that into a nice rule. What it looks like I've done is add 1 to the power, but then not just do that, then also put that number and divide by it. Yeah? So let's make it a rule. It's not a power rule, like, because we're not taking a derivative, we're going backwards. So we'll call it a reverse power rule, right? So here it is. Reverse power rule. The indefinite integral of x to the n dx, you just add 1 to the power and divide by that, and add an arbitrary constant. Now this only works when n is not -1, as you can see. Then we have 0 in the bottom, and that doesn't make sense. So this only works if n is not equal to the number -1. Okay? Let's do some examples. Now remember it now. Add 1 to the power, then divide by that. Then you'll be able to go backwards with a power of x. Okay, for example. Okay? The indefinite integral of x to the 5th. I add 1 to 5, that's 6, and divide by that. Okay? I can do that like in 5 seconds. There you go. Okay, so it's easy to do that. Let's do another one. How about the indefinite integral of x to the 1/2? Well, I could do that. Add 1 to 1/2, you get 3/2. Let's do it slow. So you add 1 to, you divide by 1 plus 1/2, and you add 1 to the power, and add an arbitrary constant, like this. Okay? Now let's clean that up. That's 1 over 3/2 x to the 3/2 plus a constant, because 1 1/2 is 3/2. And now 1 over a fraction flips it, so it's really 2/3 x to the 3/2 plus a constant. And there you have it. You are thinking backwards. Let's do another one, but now I'm going to do it fast. I'm not going to do it in 3 steps. I'm going to do it in 1 step. You ready? How about the indefinite integral of x to the How about 2/3? Well, let's see. Add 1 to 2/3. You can write the 1 as 3/3. 3/3 and 2/3 is 5/3. Then divide by 5/3. It'll flip and become 3/5 x to the 5/3 plus a constant. Yeehaw. It's very easy. Kidding me? It's easy to think backwards. Okay. Now let's look at some properties of this indefinite integral. Well, since it's the reverse of taking a derivative, it will do what the derivative does. In other words, it will ignore constants when they're multiplied by functions, and it will come into sums, because his reverse, his inverse, if you will, the derivative does those things. This is just taking derivatives in reverse, doing the inverse of taking a derivative. So here are some properties. There's two to speak of, really. Property 1, if you take the indefinite integral of a constant times a function, well, the indefinite integral, like his inverse, the derivative, remember we're just doing derivatives in reverse, will ignore the constant and just go to the function. Yeah? Oops, let me write that again down here. Yeah, this paper is a little thin here. Let's write it down here. If you take the indefinite integral of a constant times a function, like I said, his inverse, the derivative, ignores the constant, so he will. He ignores the constant and just goes to the function. Okay? There's property 1. Okay? Property 2, the derivative goes into sums. So his inverse, the indefinite integral, will too. It's just doing the derivative in reverse. So the indefinite integral of a sum or difference, differences really are sums, but anyway, is the sum or difference of the indefinite integrals. Okay? So using these properties, we can take the indefinite integral of a lot of other things now that look a little more complicated. Ready? First, let's start out easy. Let's do some trig functions. So these are more examples. How about the indefinite integral of cosine x plus 3? Okay? Well, by the property, it will come into the sum. So that will equal the indefinite integral of cosine x dx plus the indefinite integral of 3 dx. It's by the property. And now, what differentiates to be cosine? Do you know? Not take the derivative of cosine, but what differentiates to be it. So you're thinking backwards, and that's of course sine x. And what differentiates to be 3? 3x. And add your constant. And congrats. Okay? Let's do another one. How about the indefinite integral of sine x plus, say, x to the 6? Well, again, the indefinite integral by the property will come into both pieces. So it'll be the indefinite integral of sine x dx plus the indefinite integral of x to the 6 dx. And now you got to do these integrals, baby. Okay, so what differentiates to be sine? And be careful, do not say cosine, because cosine differentiates to be minus sine. We just want a sine. It's minus cosine. Ouch. Plus, and now we got a reverse power rule. Add 1 to 6, you get 7, and divide by that. And congratulations, you did it again. You thought backwards. Okay? Let's do another one. How about the indefinite integral of secant squared x plus 3x to the minus 4th? How about that? Well, again, the integral comes into each piece. Now, I'm not going to bring it into each piece like I did here, and also I did here. I'm just going to bring it in my head and do those integrals. Okay? So the integral comes here. What differentiates to be secant squared? Tangent x. And remember, here we got a reverse power rule. So add 1 to minus 4, you get what? Minus 3. And then divide by that minus 3. It cancels with this 3 and leaves a minus x to the minus 3. And then add your constant. Do another one. How about the indefinite integral of x to the 5th plus 2 divided by 3x squared? Now be careful, this is not a reverse power rule, because this isn't a power of x. So before I integrate it, I'm going to clean it up a bit. So notice you can write this as, so the integral sign's still there, x to the 5th over 3x squared plus 2 over 3x squared. Okay? And now I can clean both of these up so they really are powers of x. Okay, so I get the indefinite integral of 1/3 x to the 3rd, subtracting exponents. And here I get 2/3, and then I can write 1 over x to the 2 as x to the minus 2. And only now can I use the reverse power rule, because these are powers of x. By the property, the 1/3 will be ignored, and the integral just comes to the x to the 3rd. So add 1 to 3, you get 4, and then divide by that. By the property, the 2/3 will be ignored, and the integral comes to the x to the minus 2, which is a power rule. Add 1 to minus 2, you get minus 1, then divide by that, and add your constant. Clean it up. It's 1/12 x to the 4th minus 2/3 x to the minus 1 plus a constant. Okay? Let's do another one with some trig functions. How about this one? The indefinite integral of secant x tangent x plus 2/3 x to the 4th. How about that? Again, the integral comes to the sum. When the integral hits the secant x tangent x, what differentiates to be that? Secant x. So don't take the derivative, do the derivative in reverse. And here the derivative ignores the constant by our property and goes to the function, which is a power rule, a reverse power rule. Add 1 to 4, you get 5, then divide by 5. That 5 hits the 3 and makes 15. 2/15 x to the 5th plus a constant. See how rapidly you can do this? Okay? Okay. Now, why am I asking you to think backwards? Why? Well, because that's how the actual area can be found, by thinking backwards, without taking the limit of that sum. And that's called the fundamental theorem of calculus. Fundamental theorem of calculus. And it has two parts. It says this: let f of x be a continuous, has to be a fairly nice function, so continuous function on some interval, say a, b. Okay? Then it claims two things. Widen this out a little bit. Okay? Then it claims two things. Thing one. Now this is a very interesting thing. Okay? It's quite fascinating. We can make a function out of this function f of x. How could we do that? What we could do is take more and more of its area. Yeah? So I'm going to make a function out of this function f of x that spits out areas under f of x at progressively bigger and bigger intervals. So I'm going to call it the integral, the definite integral from some number a, how about this number a here, to random numbers x of our function. So remember what this is. This is an actual area from a to a number x under our function. That's what we agreed to call it in the last video and at the beginning of this one. And as you vary this x up here, you get area from a to x. And as x gets bigger, you could be getting more and more area. Okay, or less and less if the function's decreasing. Okay, well then that means you can now take the derivative of this function. And remarkably, it's easy to do. You just replace this x in for the t, and you get f of x itself. Now if you want to see the proof of this, the proof is in the book. And so you can read it if you want. We won't prove this, we'll just use it. Okay? There's no time to really prove these things for you. And the second statement is how we'll find actual area. So it has two parts. Okay? So now we've agreed to call the actual area under f this symbol, the definite integral from a to b of f of x dx. And now we're saying you can find that now without taking a limit of a sum. What is it equal to? Well, it's equal to capital F of b minus capital F of a. What's capital F? Well, I'll tell you. Where capital F of x is any, I repeat, any function that differentiates to be f, little f. I'll say that satisfies the equation. When you take the derivative of it, you get little f. Ouch. Okay? So I'm going to do some problems using part 1 and using part 2, and then give you some. You ready? Okay, so take a good look at part 1 now. It's a weird kind of function. It's a function that spits out area. And we are differentiating it. And it's just the original function again. Okay? So let's use the part 1 a couple times. Okay, so for example, how about these? How about let's take the derivative of the definite integral from 2 to x of this function, the square root of 1 plus t squared dt. Let's take the derivative of that. Well, remember, by the fundamental theorem, a lot of people of calculus, a lot of people call that FTC, fundamental theorem of calculus. Part 1. We just take this x and put it in there. Ouch. So it's just the square root of 1 plus x squared. Congrats. Let's do another one. How about the integral from negative 5 to x of sine t dt? let's take the derivative of this function that spits more and more area out under sine as you change the x. Well, again, by the fundamental theorem of calculus, part 1, we just replace this x into the function, and the derivative of this function is just sine of x. Now let's do a trickier one. Okay, those are easy, just using the statement as it stands. Now let's do a trickier one. How about let's take the derivative of the integral from 3 to x squared. Same function, sine of t dt. Let's take the derivative of this function. Well, be careful. Notice that this is not an x here, so let's not pretend it is. And if you look at the fundamental theorem, it's only phrased with an x there. I'll remind you right now. You ready? Here it comes. Get ready. There is just an x here. Do you see it? Okay, do you see it right there? So we are dealing with a different creature right now. You see, there's an x squared here. But fortunately, this is a composition of there being just an x here, the function with there being just an x here, composed with x squared, producing the function you see right now. By golly, this is a composition. But then that means we can use the chain rule. Okay? So realize it's FTC and a chain rule, because this thing is a composition of the one in the fundamental theorem composed with x squared. Okay? So it's the derivative of the function doing the eating, which is not seen here. It's the one with just an x here. And this derivative is just put the x into this function, and we did it up here. It's just sine x. But don't write that. Feed in the function he was eating, untampered with. Okay, sine of x squared. Don't stop there. Now times the derivative of who he was eating. Well, that was x squared. His derivative is 2x. And congrats. So you can see a chain rule can be involved in this. Let's do one more involving a chain rule. How about the function being the integral from -4 to x to the 4th plus 2x of, say, secant t dt. And let's take the derivative of this function. Okay, so these are all derivatives now. Okay, well again, there's not an x here, okay? So it's the one with an x here composed with x to the 4th plus 2x producing the one you see here. And so we can use the chain rule in combination with the fundamental theorem of calculus. Okay? Okay? So it's the derivative of the function doing the eating, which you don't see here. It's the one with just an x here. And its derivative is putting that x right here by fundamental theorem of calculus, part 1. Okay, so that would be secant x, but don't write that. Into that function, feed who he was eating, that function was eating, untampered with, and that is what's in the circle. Okay, so secant of x to the 4th plus 2x. Don't stop there. Then times the derivative of who he was eating. Well, that will be the function in the circle. And that will be 4x cubed plus 2. And it is just that easy. So some of the problems are going to ask you to do this. Okay, now let's use the fundamental theorem of calculus, part 2, to find these actual areas. I'll remind you what it says. So that's how to use part 1. Okay? Now let's talk about part 2. Because you can see this is the actual area under F. Okay? Remember, that's what we agreed to call it in the last video, this symbol. And in the beginning of this video. Okay? And verbally it's called the definite integral from a to b of f. And he says, It could be found by taking any function that differentiates to be f, shoving this number b into it, shoving this number a into it, and subtracting. Oh my gosh. You kidding me? Instead of take the limit of that sum. Well, let's do it. Let's do some. Okay, so for example, let's do some definite integrals now. In other words, actual areas, baby. Okay? So for example, let's do that guy that we did that we estimated. Remember, his area was between 6.75 and 10.75. Do you remember him? That was in the last video in 4.2. We used 4 rectangles and we used a right-hand endpoint and a left-hand endpoint and got an upper and a lower bound. Let's find the real area because we know it's in between those two numbers, baby. Okay, so let's do this. What if someone said this? So here's an example. Find the actual. So they won't say actual, they'll just say area. But I'll just remind you, we're actually finding the actual area, not estimating it. Under the function y equals f of x equals x squared from x equals 1 to x equals 3. Now if you recall, we estimated this in 4.2. Yeah? So I'll say recall. In 4.2, we saw the actual area is between 6.75 and 10.75. Remember that? Okay, let's find the actual area. Okay, well, actual area, I'll just say area now, okay, is going to be, remember what we agreed to call it. It's going to be the definite integral from 1 to 3, put your function in, dx. Now, how to do this? This is a limit of a sum, depending on if you do right-hand endpoints or left-hand endpoints, which sum. They both converge to the area. Okay, but we don't want to do that, so we want to use the fundamental theorem of calculus, FTC, Part 2, fundamental theorem of calculus, Part 2. So it says I can find anybody who differentiates to be this, shove a 3 in, shove a 1 in to him, and subtract. Kidding me? Anybody that differentiates to him? Okay, I'll just use a reverse power rule. Add 1 to 2, you get 3, and divide by 3. So here's a guy that differentiates to x squared. Now we put a bar here saying we're going to prepare to put the 1 and the 3 in and subtract. Okay? So remember, put the 3 in. Remember who goes in first? The b goes in first, that's 3, minus the a going in, that's 1, into your function right here. Okay? Work it out. That's 27 over 3 minus 1 over 3, and that is 26 over 3. And you can leave the answer like that, but just to see where it falls in our bounds up here, let's say what the actual decimal is, and it's 8.67. Okay? And so you can see it really does fall in between our bounds, except we now have the real area here. Yeah? Okay? Okay, let's do a couple more. How about, now be careful. Doing this procedure doesn't always give area. You know, if the function's sometimes over the interval, if you look at x squared, it's always up in the air. It's always positive over the interval 1 to 3. Yeah? You just found that area. Okay? There's x squared. Okay? But I'm saying if the function is not positive over the interval, then this number might not come out to be the area. Okay? Because some of the heights of your boxes could be negative. Remember, we're using function values for the heights of these boxes. Yeah? And so let's do an example like that. Okay? Showing that this number you get isn't always someone's area. It's only someone's area if the function is positive up in the air over the interval, like x squared was. Okay? Here's a guy that's sometimes up in the air and sometimes above the x-axis. That's what I'm calling up in the air. And sometimes below the x-axis. So the definite interval isn't his area. Okay? It's just a number in that case. Okay, let's do an example like that. Here's an example. Let's compute the definite integral from -2 to 1 of x cubed. Again, the fundamental theorem of calculus says that I can take anybody that differentiates to bx cubed, shove a 1 in, shove a -2 in, and subtract to find this definite integral. Okay? So I'll use the reverse power rule. Add 1 to 3, you get 4. Divide by 4. And put a bar there saying you're preparing to put the numbers in on the next step. Okay? Then on the next step, put the numbers in. Remember, the top number goes in first, minus the bottom number going in. And compute. 1 to the fourth is just 1. So here you get a fourth. Minus 2 to the fourth is 16. So you get 16 over 4. Yeah, and that's minus 15 over 4. And you can see it's negative. So that's definitely not area. Area is never negative. Ouch. But, like I told you, if you look at x cubed, here's a graph. You see it's up in the air and down sometimes. Up above the x-axis and down below the x-axis. And if you look at it on our interval, -2 to 1, you can see that it's below the axis more than it is above the axis. So that the rectangles we put under this function have negative heights here and positive heights here, and there's more with negative heights than positive heights. And so when we add them all up, which is what we're doing, and take the limit of that sum, we get a negative number. So be careful, it's not always area. Let's say that. It's not area, it's just a number sum in a lot of cases. Okay? It's only area when the guy is fully above the x-axis over the interval. Otherwise, it's just a number. Let's do another one. So it could come out to be negative. It can even come out to be 0. Here's an example of that. Let's compute the definite integral from minus pi over 2, for all those scared of trig functions, to pi over 2 of sine x dx. Okay? Well, again, according to the fundamental theorem of calculus, all I need is a guy that differentiates to be sine x, and that is, of course, cosine x. And then shove the two numbers in and subtract. And of course we write a bar here saying we're preparing to shove the numbers in on the next line. Okay, so put a pi over 2 in. And then minus, putting a minus pi over 2 in. Okay? Now, we know the unit circle. Pi over 2 is 90 degrees. The cosine here is 0. Minus pi over 2 sits in the same place as 3 pi over 2, 270 degrees. And again, the cosine is 0. And so you get 0. Okay? So be careful. It's not always an area. Let's have a look at the graph and see what happened real quick. Only takes like a fraction of a second. If you look at sine x, it looks like this. But if you look at minus pi over 2 to pi over 2, there's as much negative height boxes as there are positively height boxes. or rectangles rather, that we would be putting under this, and they cancel each other out, producing 0. So it's not an area, okay? It's just a number in this case. Be careful. The function needs to be fully upstairs over the interval. Like, for instance, this one. One more, then I'm going to give you some. For instance, this one. Let's say it is a word problem. Find the area under the function y equals f of x equals cosine x from x equals 0 to x equals pi. How about that? Okay? Well, if you look at this function, cosine x, it looks like this. Yeah? Goes up as high as 1, down as low as minus 1. Okay? And if you look at, here's pi over 2. Oh, let's say pi over 2 here, sorry. Pi over 2, because we want to get an area, not just a number. So let's change it to pi over 2 here. Okay? So if you look at pi over 2, it's right here. Here's pi, it's -1, it's 0 at 3 pi over 2, and it's back to 1 at 2 pi. The cosine of 2 pi is 1. And so if you look, it really is positive over this interval, 0 to pi over 2. So we know we're going to get area this time, not just a number. So the area is, make the computation, baby. We've agreed to call it the definite integral from 0 to pi over 2 of our function dx. By the fundamental theorem of calculus, part 2, we can evaluate this by finding any guy that differentiates to be cosine x, that would be sine x, and put the numbers in and subtract. So we put a bar there saying we're prepared to do that, and then we put the numbers in. So it'd be the sine of pi over 2 minus the sine of 0. The sine of pi over 2, that's 1. The sine of 0 is 0. And congratulations, the area is 1 square unit. And that is your area here. It's your area. Okay? So some of the problems are just going to ask you to do a definite integral, whether it's area or not, and others are going to ask you one that happens to be someone's area. So with that, and also using the fundamental theorem of calculus part 2. And also some of the problems are going to ask you, just like we did before now, to use the fundamental theorem of calculus part 1. With that being said, let's give you the problems. In 4.3, the problems are 7 to 17 odd. These are all using the fundamental theorem of calculus part 1. And we did enough examples where it's but easy. And finally, 19 to 35 odd are all using their definite integrals, the fundamental theorem of calculus part 2. Okay? So there's your problems. Just doing what we did on various functions. Okay? With that being said, I'll see you in the next video.